So I'll start with the definition. So we have the following situation. Two functors, f and g, are functors between categories C and D. So functors. And a natural transformation between functors. So notation for natural transformations, I'm usually going to use some Greek letters, for example, alpha. So we can think about this as a maps, and notation is double arrow. So this is notation for natural transformations, and this means the following. So this natural transformation consists of the following data. So first of all, I have an arrow, say alpha x, from f of x to the g of x. So this is, of course, a morphism in the category D, and this is for any object x in the category C. Okay, so you can think about this as kind of as a map of functors, but what it means that this is just a natural transformation, not just any transformation. Well, it means that I have the following commutative square. So I can take one object. For one object, I have such a map. So then I can take another object, say x prime, and fix a map. So say I have map f from x to the x prime. Then I have the induced maps. So here this will be a capital F applied to the little f, to the f of x prime. So here I have my map for any object x, so I have map for the x prime. And this goes to the g of x prime. And here, of course, I have an arrow g of the f. Okay, so this is a bunch of transformations, so a bunch of arrows for every object in the category C, such that all such squares are commutative. And the commutativity of such squares is exactly a condition of naturality of a transformation. So for any f like this in the category C. So if you want, I can write this as for any f in the C of x, x prime. Okay, so alpha is called natural isomorphism if, well, of course, if this is natural transformation, and for any x, alpha of x is invertible, and we can even write the inverse of this. Well, this is just alpha inverse for the object x. Well, for natural transformations, we have compositions. If I have two natural transformations, say alpha and beta from f to g, well, then clearly I can define composition, and I only need to say what it is on the object x. Well, by definition, this is alpha of x, and I take composition with the beta x. So very, very straightforward definition of the composition. And of course, for any functor, I have identity natural transformation. Well, can you guess the definition of the identity? Well, here, this is the identity. And of course, if you plug in any map, this will be commutative. And more notation. So when I fix two categories, well, you can see that in these definitions, we can form a category such that objects are functors, and morphism between functors are natural transformations. So I need some notation for this category. So notation. If I fix categories C and D, I can consider functors between C and D. This is one possible notation, but this is not the kind of the standard notation in category theory. The standard notation will be this one.
Sorry, so I don't understand. Compositions, it's supposed to be three categories, right? A functor from F to G.
Oh, yeah, you're right. Yes, 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 yes. So let's say that I have functor alpha,
G, H.
yeah, f to g, and another functor beta g to h. Well, does this work? Well, I think I need to do this the other way around, right? So I need this to be beta, and I need this to be alpha. Then I can compose them. Okay, so this is our notation for the functors, and of course, as in the set theory, there's a short notation, all functors from C to D. We just use this exponential notation.
Should we write them consequently instead of значок следующий?
Где там двойная стрелочка?
Ah. Well, the notation for the natural transformations is this right notation in the definition, and I promise you I'm going to usually write just the usual arrow, because I can't remember when I need to write this for the natural transformations. No, for any categories. Just a short notation. And, well, there's even more notation. So sometimes people write nat for natural transformations between two particular functors, f and g. So this is exactly the same thing as the home set. And for the home sets, well, we just use category itself. So this is this. So I hope this still makes sense.
What is this notation? It's the
Not?
no, the previous one.
Well, this is all functors as a category. So maybe I need to underline it as a category. So affixed to categories, consider objects are functors, maps are natural transformations. So have this category. Well, this is one notation, not the standard one. The standard one is this one. And there's also short notation. This. When you do computations, the short notation could be convenient.
And so we go further in a recurrent way, and we want categories like of natural transformations,
We're going to return to this at the end of the lecture. So, and this is notation for the natural transformations. Well, this is the home set in this category. So, this is what it means. Okay, so let's consider several examples of natural transformations. Well, in the first example, you know from the algebra, so you can take the category of groups, and again the category of groups, and take two functors. So take the identity functor and take the abelianization functor. So of course this is an abelian group, but I can consider this abelian group just as a group. Still works. So there is a natural transformation here. And this natural transformation is just the standard canonical surjection from the group to the abelianization of the group. It's easy exercise to check this actually natural. So this is, well, if I call this alpha, this is alpha G, and whenever you have any map between groups, you get the corresponding commutative square. Okay, so next example, I take category of commutative rings and the category of groups. So here the first functor is the GLN functor, and the second functor, I can call this GL1. Oh, and also this is what in the core algebra course is, we use notation star for this thing. It's just all invertible elements in the ring. And of course I claim that there is a natural transformation between these two functors. Well, can you guess what the natural transformation is in this case?
Determinant.
Yeah, so the natural transformation is determinant. our next example, you know, if you know some commutative algebra, so this is from our fixed R is a commutative ring. Then, if I consider modules over R, and again modules over R, and two functors, as before, one is the identity functor, identity functor, we can write just one, and the second functor is the localization functor. So this S is some multiplicatively closed subset of the R. So here we have a natural transformation, and this natural transformation is just a map from the module to the localization of this module. Now, essentially, what's the localization of the module? These are. So these are fractions of the form m over s, such that m is in the m and s is in the s. So you can think about this s as a set of denominators, and you can use these denominators to form such fractions, and you can check that this is again the module rather immediately. Well, it's not hard computation. And the map here, you just take m and send this to the fraction m over 1.
Do we assume that everything commutes here is obvious, or
In this case,
in all cases?
in all cases, I leave this as an exercise. So this is not a hard exercise. You can do this. If you understand the definition of functors, then the checking that this is everything is commutative is a simple exercise. Maybe we do one or two cases on the seminar.
So S minus 1 is morphism and natural transformation?
No, S inverse is a functor. It takes a module and constructs a new module, namely this module. So that's a functor. It's also you can apply also this for the maps between modules. And the natural transformation, the natural transformation, if I call this alpha, then the alpha m is just this map, canonical map from the module to its localization. You can always have a map like this.
Does this work for every functor which takes a module and substitute this module and some fixed module?
You want to consider functor like this, you say you fix a module n, take a tensor product like this, and how are you supposed to get a map like this?
So if it has two,
Or you kind of need at least something like maybe distinguished element in this n. Yeah. Okay, so and the other examples, so here there were examples of some individual natural transformations. So 3 examples of individual natural transformations. Now I want to find all natural transformations. Well, the simplest possible example, what if I take the following category? So let me call this 1. So as a category, this is just one object and one arrow. So can you compute this category? What about morphisms?
Is the
Yeah, so it's just C in topological way. So next example.
is there any maybe 2 lower power category which gives us c to the power of 2 is c
That's exactly will be example 5. So here I take category 2. This is just again 2 objects, say 1, and I have identity on the first object, and I have another object, and there are no maps between those objects. And I want to understand what C to the 2.
А почему при защите мере получается любой морфизм?
Well, you say essentially you just need to apply the definition. So what's an object here? Object is just a functor from this category to C. So you're just choosing where you send this object star, right? This is just choosing an object. So object in the C to the 1. This is the same thing as object in the C. Now you need to understand what's the natural transformation. Well, what are maps in this category? What are natural transformations? So natural transformations, well, so what you have? You have, say, one. Well, if you return to the notation from the definition, you have one functor, say f. This is from the star to the category C. Another functor, this is from the star to the category C. So what's the natural transformation? Well, that's a map. I need to fix an object in the first category. There's only one object, so I don't need to fix anything. So this will be a
What is star again?
star is just an object in this category, unique object.
Okay, but isn't
Okay,
so it's the same as right, just one, yeah?
this would be the correct notation. So essentially, instead of f of star, I can write everywhere an object. So let me maybe call A. So then I have f of g of star. So let me call this B. And a natural transformation is a map here, right? Now I need to check that some square is commutative. So what square is commutative? Oh. Yeah, so essentially there is no square because here you get identity, and exactly the same map. So the condition is just vacuous. Okay. Well, it's actually not a good thing because here what I'm writing the isomorphism of categories, but I haven't properly defined isomorphism of categories yet. But you can see what it actually means. It means, well, you have functor in one direction, functor in another direction, and both compositions are the identity functors. And what's the answer here? Yeah, and the proof is more or less the same. You just need to understand the objects and again the morphisms. Okay. Example 6. Now I want to take the following category. So let me maybe call this I. So this is the category with two objects and two arrows. Let's continue to use notation star 1 and star 2. So of course we always have identities, so I'm not going to write identities. There's identity here, but non-trivial morphisms are these two. What is this category? Yeah. This is exactly the category of graphs. Do you see why? No, what's a graph? Graph is two sets. A set of vertices and set of edges, right? Directed graph. And for any, so say the graph gamma, this is set of edges, vertices, and whenever you have an edge, you can compute two vertices, the beginning and the end. So it means that you have two functions, S and T, and these are functions from the edges to the vertices. So that's the directed graph on this in the category of sets. And exactly such objects you get if you consider natural transformations here.
Excuse me, did you say what is the isomorphism between categories?
I mentioned that I'm using this all the time, but I haven't defined this. Maybe I can define it right now if this causes some problems.
Sorry, what's this map from edges to vertices?
The beginning and the end. source and target, hence S and T. So definition, categories C and D are isomorphic if, well, there is functor in one direction, there is functor in the other direction, such that, or maybe such that when you take composition F and G, you get the identity functor. So this G starts here, so this is identity on the D, and in the other direction, you get identity on this C. So that's the definition of an isomorphism. Notice that these functors are equal as functors. Okay.
By equality, you mean that they are naturally isomorphic?
No, I mean that they're equal. Equal as functors. This is a big difference between isomorphism of categories and equivalence of categories. And equivalence of categories, that's exactly what we're going to do next when we finish this set of examples.
Что такое морфизм в категории графа?
No, that's a map of edges, maps of vertices, such that they commute with these maps. For any vertex, you associate a vertex. For any edge, you associate an edge, such that source and target are preserved for any map. And one more example that I mentioned on the first lecture. So with any group, we can associate a category. Let's call this G underlined. So this is as a category. Again, it has one object, and the arrows in this category are just elements in the group G. So G is in G. Do you see what this category is? Mm-hmm. And notice that this is a group is not important. The same is true for any monoid.
G sets.
No, G sets I defined last time. So objects are sets with an action of the group G, and the maps are equivariant maps. And you can see that this is precisely the condition. Again, what are objects here? You have only one object in the first category, so the object is just choosing a set. And the morphism between two such sets is exactly an equivariant map, because the commutative square in this category that defines natural transformations is exactly equivariant condition for this category. Again, maybe that's an exercise that we need to do in a seminar. And this example has many variations. If you want, you can say that you take the category of vector spaces and try to compute this category of functors. So, as you can guess, this is exactly a representation over field K of the group G. And maybe one more variation of this: take abelian groups, take a ring, consider the ring as a category with one object. So can you guess the answer here?
How do we consider a ring?
In exactly the same way as with the groups.
But we have two structures.
Yeah, we have an additional structure, but it's not really important. Well, actually, it is important. But if I want to say that all the maps are kind of map sums to sums, then I need to consider functors here, which are additive functors. So maybe
We're yet to know what is the active functor category.
maybe we just postpone this example. But the answer is still true. So you need to consider not just all functors, but additive functors. And additive functors just means that here on the home sets, there's not just sets, these are abelian groups. So the map on the home sets respects this addition on the home set. So respects the structure of the abelian group. Additive functors. We're going to return to this later. Since we need these additive functors, so we postpone this example.
So it's not just R2.
No. So equivalence of categories. So this notion of the isomorphism of categories is too restrictive, because if you return to this definition, well, you can see that at least from this definition you can see that there is a bijection of the objects in the two categories. And if you fix two objects here and two objects here, and the images on say under the functor f, then the home sets are again bijective. And usually we don't want to have this in our examples. We want categories kind of to be different, but equivalent in some other sense, well, in the sense that I'm going to provide right now. So categories C and D are equivalent. Again, the correct notation is this one, but I probably cannot keep this correct notation all the time. So if we have two functors as before, so f is a functor from C to D. There is another functor g in the other direction. And we have the condition that g composition with f has a natural transformation, which is an isomorphism to the identity functor. So I'll start with the f. So this is identity on C. And in the other direction, there's a natural isomorphism with the identity functor on the D. So equivalence of categories is an isomorphism up to isomorphism. What would be a typical example of two equivalent categories? So I can take, again, one object and one arrow and another category, so this is C. And the category D has two objects. Oh, identity, which is not really an interesting information. But now I have two arrows, F and the inverse of F, F inverse. So these two objects are isomorphic. So I claim that these two categories, of course, are not isomorphic because there is no bijection on the sets of objects, but these two categories are equivalent. Do you see the equivalence?
Естественный изоморфизм, к которому вы летите, это который естественный изоморфизм получается?
So it means that for any object, if I take any object, I can compute this composition. Like I can take just this object, and there is an isomorphism, which is natural. So how to set up functors f and g in this example? One? Two. Yeah, you can take this thing and embed this, say, as the first copy, or embed this as the second copy, and another direction, or we can just take, say, if you embed this as the first copy, take this first copy and map it back to this copy. So that's a typical example of two categories which are equivalent but not isomorphic. Okay.
Тогда получается, что естественный изоморфизм определены фактически не только на функторах, да, потому что одно из этих произведений не функтора, у него нет.
what is not a functor. No, everything here is a functor.
What's natural isomorphism again? Like, so it's
So that's a natural transformation such that for any object x, the map that I called alpha x is an isomorphism in the category D. So in the lemma we have the following situation. So I have a functor f from the category C to the category D, and I have an embedding of a full subcategory. So D naught is embedded into D, and the embedding function I'm going to call iota. So D naught is a full subcategory such that I have the following property. For any object x in the category C, there is object y in the category D naught such that f of x is isomorphic to the object y. So essentially this functor has a property that its image up to an isomorphism is in the D0. So then the conclusion, so then there is functor f naught from the C to the D naught, and an isomorphism of functors. Let's call this theta naught from f. Well, again, this is a natural transformation to the composition of the iota and f naught. Okay, so if you have this property that the kind of if image is in the D0, we can decompose this functor in the composition of two functors. D naught, so this is iota, and this is f0. And we have trivial uniqueness properties. So moreover, if we have theta 1, another isomorphism from f to the composition of the iota and some other functor f1, so then there is unique isomorphism theta of the two functors f1 and f0 such that theta 0 is the composition of the iota composed with the theta and then composition with the theta 1. Okay, so the proof is based on the axiom of choice. So by the axiom of choice, for any object x in the category C, well, I can choose y in the objects of D0 and an isomorphism. So let's call this isomorphism phi sub x. So this will be an isomorphism from y to the f of x. So now I need to define functor f0. So I need to define f0 on objects and also on the arrows. So on objects, so what if I want to define f0 on x? So do you have any ideas? What would be the right definition of f0 on x? Mm-hmm. And what is f0 on some map f? Say if I have map f from x to some x prime. So what's the definition of the f0 on f?
Well, it should be a composition.
Of what?
Well, we take y, we take phi x, then f of f,
Mm-hmm.
and then phi x prime inverse.
Yeah, so this is the following composition as was correctly suggested. So this will be okay. So maybe to begin with, I just write that this is from f0 of x to the f0 of x prime, and this is defined so as the following composition. So I start with f0 of x, so which is y. Hence, I have a map phi sub x to the f of x. Here, I know that there is a map f of little f. So this will be to the f of the x prime. And then I need to take the kind of inverse.
Sorry, what is written on the second line? And we choose y and
And the isomorphism, this one. This is the isomorphism. With any object y, we choose also this isomorphism.
and what is x star or x0 f small f from x to x prime?
So this is just notation for the map, and I want to define this functor f0 on this map. So this is supposed to be a map from this object to this object, and it is defined as the composition of three maps. And of course, because this is an isomorphism, you can invert this, and there is a map in the other direction. And essentially, this is the proof of this statement, because now we need to check conditions that this f0 is actually a functor, but this is not very hard. So if you just look at the definition, you immediately get that the f0 of the identity morphism is again identity morphism, because we know this property for this map. You get identity here, and then you get the composition of the isomorphism and the inverse of this isomorphism. So that's the identity. And do you see that this functor maps composition of maps to the composition of maps? Again, essentially, you need to apply the definition. Right? If you, for example, try to compute the right-hand side, you get one such diagram, you get another such diagram. This phi and phi inverse in the middle, they cancel. Then you have property f, that this maps compositions to compositions, and you get from the right-hand side the left-hand side. And this moreover part, I'm going to leave this as an exercise because I think it's completely trivial. Essentially, what else can you do? So if you choose another functor, there will be an isomorphism relating these two functors.
And px assembled give an natural isomorphism between.
Exactly, yes, yes. And again, this follows from the definition of the functor. Well, I think this is more or less immediately.
So what about f0 and f of r? Like, do we construct them or what else?
Well, this moreover part, as I was saying, this is a trivial part, because if you want to construct, well, suppose you want to get another functor f1. Well, this just means that you do essentially the same construction, or you just, well, well, for another functor, well, okay, so since we know that we have this condition that any object, so what's the condition? So that any object there is this y, right? So if you have another functor, then this y will be, well, if you assign f1 to this object to be some y, and for any y there is an object such that we have this condition, so this means that there is an isomorphism between f0 of x and f1 of x.
But that's if f1 of x is actually isomorphic to some degree, right?
Which are still isomorphic.
Yeah, so you claim that if we have like some other function, let's say f1,
Yeah.
then
So suppose you have some f1 and you want to compute this on the element x. So this will be some, say, y prime. But this y prime has to be isomorphic, still has to be isomorphic to the f of x. So you combine together these two isomorphisms, and that will be natural isomorphism. You can check this if you want. Okay, so for any category C has a full subcategory Sk of C such that first of all the embedding of the Sk of C to the C is an equivalence and the second property is that if for any, well, if you have x and y in the Sk of C and x is isomorphic to y, then x is equal to y.
SKC is a notation, right?
Sk? Yeah. So this kind of operation that you apply to the category C. Oh, this stands for the skeleton. This is the skeleton of the category C.
So, can I ask a question?
Mhm.
What is the meaning of the previous lemma? What does it mean?
Well, it means that whenever you have a functor such that if you know that the image of this functor is in some subcategory, you can factor this functor into two functors. One is in the, it's just a kind of functor to the to the subcategory, and then the second factor is just the canonical embedding of the subcategory into the category.
Restrict this functor in this way.
No, that's not a restriction, right? We can,
And is the skeleton unique?
no, of course not.
Introduce
No.
Maybe in some subtle sense.
Well, it's unique up to equivalence, but this is kind of trivial observation.
Yeah.
Well, you can think about this as a technical lemma that we need to prove the second lemma, which kind of has meaning, kind of clear meaning, right? You can start with any category and replace this with the equivalent category such that there are no non-trivial isomorphisms in this new category. And this lemma will be a step for the next theorem. Okay.
Full subcategory means that the embedding factor is full.
You can say it this way, yes. Also, full subcategory means that you just to choose some objects, and the homesets on these objects are exactly the same as the homesets in the category C. So by axiom of choice, again, I can choose one object in each isomorphism class of the category C, and just define skeleton of C is the full subcategory is the or consisting of such objects.
Do any kind of set theoretic issues arise here? Because we apply the axiom of choice to something which doesn't seem to be a set.
No, there are, of course, the set theoretical difficulties.
But we just ignore it because it's not the essence of what we're doing.
Yeah, that's one answer. So the problem is that isomorphism classes is not necessarily a set. So for example, you can say that we work with the small categories, and the small category means that the objects in the category form a set. Then there are no problems. Otherwise, you need to say in what sense axiom of choice is kind of meaningful for a class, not for a set. Okay. So
Какое последнее слово в предпоследней строчке?
consisting of such objects. So in each isomorphism class, we choose an object by axiom of choice, and then just kind of consider a subcategory. Objects are these objects, and morphisms are exactly the morphisms in the category C.
Question, like, yes, we assume some equivalence classes, like, what's the mean? So we need to, like, x is equal to y if y. If it's equal, I just don't understand the
Isomorph.
So here we have the isomorphism
bit higher, like in the lemma.
in the lemma. So the statement that this is an equivalence of categories.
Okay.
So this category is equivalent to its skeleton. And moreover, in the skeleton, we have the property that whenever we have two objects, and we know that these two objects are isomorphic, actually they're equal. Okay, so and then we do the following. We take the identity functor from C to the C and apply previous lemma. So by previous lemma, we can write this identity on the C as the composition of the embedding, so iota, and well, some functor. So let's use notation as before. Let's call this functor f0 as in the previous lemma. Right? No, not equal, but isomorphic, of course. Iota is given in the statement of the lemma. And f is just some functor that exists by the construction of the previous lemma. So the lemma that was on this blackboard. Yes. Yeah, previous lemma, yes.
The lemma before that is
No, this is the lemma we're currently trying to prove. The previous lemma is the lemma before that. We haven't finished the proof of the lemma. We don't know. Of course, we have this second property immediately follows from this construction. We don't know that this embedding is an equivalence. So we see that there is a functor in the other direction. And so now f0 goes in the other direction. And we see that this composition is the identity on C. So we only need to show that the composition in the other direction is identity on this skeleton. Well, no. I don't know how I wrote this. This is not a functor from C to C, it's a functor from C to the skeleton of C. Okay. Now let's do this computation. So I take composition of the f0 and iota and compose again this with iota, use the associativity to rewrite this as this composition first, then composition with iota. Now for this composition, I already know this is isomorphic to the identity. So this is isomorphic to the identity on the C composition with iota. So this is isomorphic to the iota. And finally, iota is isomorphic to the iota composition with the identity on the skeleton of C, right? By trivial reasons. Now a claim to finish the proof is that I can drop this iota and say that I have this isomorphism. Okay. Skeleton C. So do you see why I can drop the iota from the formula? Yes. Exactly. Because iota is just a full embedding of a subcategory into a category. It means that, well, if you have an isomorphism here between, suppose you compute the left-hand side and the right-hand side on some object. You have an isomorphism here, right? And because the iota is fully faithful, well, you can say that this isomorphism is iota of some isomorphism. And the commutative square that you have is also iota of commutative square for these two functors. Commutative square for neutrality. Okay. Finally, the theorem. So equivalence is the same thing as fully faithful plus essentially surjective. So a functor f from C to D is an equivalence if and only if f is fully faithful. For shortness, I'm going to write ff, and essentially surjective. So now with the help of the previous lemma, the proof is completely trivial. So of course in one direction this is clear. If you have an equivalence, these two properties are clear. In the other direction, well, I have skeleton of C. So this is embedded into the C. Let's call the map in the other direction JC. And I have the same for the second category D. Right, so this we know from the previous lemma. I just give a notation for the functor going in the other direction, j. So before it was f0. And I give notation C and D because we have two categories, C and D. Okay, so here we have some functor f. Well, we have an equivalence of two categories, skeleton of C and C. So in one direction, the functor is just the embedding, and there is a functor in the other direction from the definition of the equivalence of categories. Actually, there is a name for this functor. This functor, if you have an equivalence, say C and D, and this is an equivalence given by two functors f and g. G is called quasi-inverse to the f, and f is quasi-inverse to the g. So with this terminology, I can say that the j is quasi-inverse to the I, or iota. So of course here I have composition, so j, d, composition with f, and composition with iota c. Check this formula, I think that's correct. Right? So I'm going like this, and back like this. But here, this is an isomorphism of categories. So when we go to the skeletons, there is no difference between equivalence and isomorphisms. So composition of the J, D, F, and iota C is an isomorphism. So there is inverse. So K, it's inverse. Then the composition of the iota C, K, and the JD is quasi-inverse of F. So that's the construction. Well, that terminology that I defined here. So if you have an equivalence of categories C and D, this is realized by two factors, F and G. And in this situation, we call G quasi-inverse to F and F quasi-inverse to G.
There are two categories and equivalence.
Yeah, and equivalence, which means that we have one functor, another functor, have natural isomorphism in for one composition and the other composition. So in this case, F is quasi-inverse of G. So since it's not an isomorphism, it's not really inverse, so we call this quasi-inverse for equivalence of categories. Okay. So let's postpone some examples of equivalent.
Подождите, а почему in skeletal categories equivalence is isomorphism?
Oh, because there are no isomorphisms that are not just equalities. If you write, say, something like this, FG identity, right? So it means that when you plug in object here and here, you get an isomorphism, but that's just an equality. Because in this skeleton, there is no isomorphism that of the other type.
If two objects are equal, all the isomorphic objects are equal, it doesn't mean that the composition of F and G must be equal to identity as a functor. Because we still have trivial automorphisms of objects.
Well, I think what you mean that we still need to check the neutrality conditions, right?
Yeah.
Yeah.
Well, kind of,
Yeah, neutrality conditions are still true because we have neutrality conditions for the equivalence of categories. So next, let's prove Ioannidis' lemma. This is a very simple statement, but it is useful and has many applications. So, no, I need to fix some terminology. So, but maybe, okay. Before I formulate the lemma, let me fix some terminology. So let's call C underline check the category of the functors from the category C to the category sets. So then I can formulate the lemma using this notation. So if I have F as a functor in the category that I just defined, namely this is just a functor from C to the sets, so then I can take the functor HA, main functor, represented by object A, and try to compute all the natural transformations between these two functors. So HA and some other functor. And the claim is that this is bijective to the F of A, and this bijection is natural in A. This is the main functor that we defined last time, so maybe I redefine it here. So HA is a functor from the category C to the category of sets, and if you want to compute this functor on some other object B, this is by definition C underline A, B. We call this main covariant functor, and there was also a version when we fixed the second argument that was main contravariant functor.
So we said that maps are exactly the
So here we have natural transformations between two functors. And here we have just a set, which is the value of this functor on this set. So I claim that there is a bijection between two sets. And moreover, this bijection is natural in terms of objects and also in terms of functors. Well, maybe before we do the proof, do you recognize this statement? You already probably know special cases of this statement. What about the case of one object? You're probably more familiar with the groups than monoids. So if I ask you to compute hom G, G, X, so what's this?
Which category?
In the category of G sets. If you like, I can write this formally. But of course, I can do this for monoids. And that's Ioannidis lemma. And you also know something like this, hom over R, R, M, M, right? Isomorphic to M. And this is isomorphic to X. This is also Ioannidis lemma for the special case where you take one, well, category is one object, and R give you all the maps, and this is an additive category. So Ioannidis lemma is kind of statements of this type. If you compute a hom set from the very simple object, namely here this is the ring, this is the monoid, you get an answer which is given tautologically by the same object on which you apply this hom. And if you return to the proof of these trivial statements, you can see that it's exactly the same proof I'm going to give you right now. So I'm going to start with the definition of a natural transformation. So I have HA.
Что означает, что биекция натуральна in A and F?
Well, exactly the same thing as before. It means that, for example, if you fix F and you consider the left-hand side and the right-hand side as a functor of A, then this bijection, this will be a natural transformation from this functor to this functor as functor of A. And that way around, if you fix A and you consider the left-hand side and the right-hand side as a functor of F, again, this will be a natural transformation for the, well, I'm going to write precisely all the commutative squares that corresponds to this neutrality. Okay, first of all, if you have a natural transformation, it by definition means that you have the following commutative square. So now I'm just repeating the definition, right? So we have this. Now here, you have a distinguished element, namely the identity from A to A. If you return to the definition, here there is one A. That's an element in this set. So then I can do the following elementary computation. Since this is commutative, I can compute composition like this and like this on this element, and take this element and compute the other composition. So let me write this. So f of the f applied to the theta a 1a, right? So I'm starting with the identity, apply the natural transformation, and then apply this map. This is the same thing as theta b that I need to apply to the HA of f applied to the 1a, right? That's just the commutativity of this diagram computed on one particular element in this set. So can we simplify this? What's this? Yeah, this is f. So what we have is that f of f theta a on the 1a, this is the same as theta sub b of f. So this finishes the proof, up to neutrality, of course, because we can see that this natural transformation on any object and any map is completely determined by the fact that this is a functor, so we have this, so f is a functor, and by the value of the theta of a on the element 1. Right? You look a little bit confused. So I want to understand, well, maybe I simplify things a little bit if I just write the maps that I take natural transformation here, send it to something here. So C check H A F. There is a bijection with f of a. So if I take a natural transformation, where this thing is going? Mm-hmm. And okay, so clearly natural transformation completely determines this element. You just compute this natural transformation on one particular element for object A. Now, if I, for example, fix some x here in this set f of A, can I determine the natural transformation theta? So if I want to do this, I need to say what's the theta for any object and any map is, right? When I just say that this is by definition f of the little f computed on x. And that's the bijection. In exactly the same way, for example, here, everything is determined by the image of element 1. How this isomorphism works, you just take element 1, compute on this element, take a homomorphism, compute this on element 1, you get some element in the M. And the other way around, from element M, you compute the homomorphisms. Here we do the same thing. On the element 1, you compute the element from this set, and if you have element from this set, we can compute the map natural transformation. Okay. Now I want to check that this is natural in the object A. So more precisely, I need to see that the following diagram is commutative. So this is an isomorphism, as we know, with the f of A. Now I have another object B, as before, f is a map from A to B. So here I have some induced map, H, B, F, and again an isomorphism from the Unitas lemma. So let me call this capital HF.
HB to, you get only a map from HB to HA.
Well, let's check this. So if I have a map like this, then I have a map from HB to the HA, right?
Oh, but then you do it once again.
And then I take another precomposition. So H sub F, if I want to apply this to some natural transformation theta, as an notation we used before, well, this is the composition of theta and HF. So I think this works.
Извините, пожалуйста, можете все-таки вернуться к тому, как ТТА строится?
Что делается?
Как вот ТТА строится?
Когда вот это известно,
Ну, просто откуда оно вообще взялось?
well, here we have natural transformations. Natural transformations are these theta sub A maps, right? Such that such squares are commutative. This is by definition of natural transformation. So if you want to construct such natural transformation, you want to know, for example, well, well, between two functors, here we have functors HA and functors F, and kind of if you plug in any object B, you need to understand how you can construct this map here, and right? This is what you need if you want to define natural transformation. So then, this is the definition for this natural transformation. So if I fix an element, take any element in this set, call this element X, and this is how I construct natural transformation, by this formula. And I use this formula because if I go one direction, the other direction, I get the identity. So that would be indeed bijections. Okay. So we need to check that this diagram is commutative. So let's compute composition of the theta and HF. Namely, I'm going from the top left to the bottom right first. So, well, from the top left to the top right, and then from the top right to the bottom right. So this composition is this thing, right? By definition of the maps that I have here. Now, more precisely, by what we mean by composition of natural transformations, this is theta B composed with the H sub F at the element B, and then I need to apply this to the 1B. So, can we do this computation maybe one more time? What would happen with 1B if I apply HF to this element? Yeah. So this is theta B of F. And by the formula that we already derived there, this is the same thing as the F of the little f, theta A of the identity, right? But that's exactly what happens if you go like this. This will be theta A applied to the 1, and then apply F of F. So we have naturality in the A. And finally, let's check that if this thing is natural for functors. So as before, I have a commutative diagram. Well, I have a diagram that I need to check that this is commutative. Right? So if I can check that this diagram is commutative, this will be exactly a condition that this thing is natural in the argument which is a functor. But I think this is even easier than what we've done before. If I try to compute the composition, say I choose some theta here, and I try to apply alpha, so precomposition with alpha of the theta. So on A, apply to the element 1A, right? So this is what I need to do if I want to compute composition like this and then like this. Well, again, what this means that this composition at the element A is applied to 1A. So this is alpha A composition with the theta A, and this is applied to the 1A. Well, if I just change the order of the brackets, I get what I want, right? So I first apply theta A to the identity. This is this map, and then I apply alpha sub A, this map. Now this is really the end of the proof. And I think this is the end of the lecture. Well, let's take a 10 minutes break.
А можно 15 хотя бы, чтобы послушать?
Okay, 15 minutes break.
Задание сдавать, да?
А если вы решили задачу, сдавайте. Нет, это не I don't want to finish my lecture at this step, I want to give you several remarks, because it's natural to give these remarks right now and not so natural in the beginning of the next lecture. So, first remark is that it looks like that in Ioannidis lemma, this category of sets plays a distinguished role. Well, and the reason for this is that when you consider functor HA from the C, it's only a priori defined as a functor to the sets, right? Because if you compute Holmes between objects A and B, this is just a set in some category. But sometimes in some examples, you can take, for example, something like K is an algebra over field K, and then you consider modules, say left modules over A. Then in this category, if you take two modules, say M and N, then this is a vector space, and this is over field K, right? So if you have such a category where Holmes, well, not just sets, but have some other structure, like for example, vector spaces, or you can take, say, any ring, then you can say that the category of A modules, if you consider such Holmes sets, will be an abelian group. And then you still can define functor HA, but in this case, for example, this will be from the C to the vector spaces over K. So this still works. And you can formulate and prove Ioannidis lemma for such functors. So the category you would consider would be category like this, C check. This will be functors from the C to the category of vector spaces, or abelian groups, or something else.
It's called enriched category theory, right?
Yeah, you can say that this category is enriched, and the version of the Ioannidis lemma, this will be enriched Ioannidis lemma. You can Google this if you want. We probably won't do enriched categories anyway, so we just, in our examples, we just consider algebra, say, over a field, and just do computations for such particular categories, and we notice that the Holmes sets such as vector spaces, or abelian groups if this is just a ring. So this is the first remark, that sets are distinguished only by the reason that if you take any category, then the Holm is just a set and nothing more. But if you have some additional structure, you can you can prove some more interesting versions of the Ioannidis lemma, where you have some isomorphism, not bijection of sets, but isomorphisms of vector spaces, isomorphisms of abelian groups, etc. Okay, second example is the following observation. Second remark is the following observation. We have functor from C to the C check. So this functor takes an object and sends this to the representable functor HA. Thank you. So if I now, in this category C check, want to compute the Holmes sets between two such functors in the image of this. By the way, sometimes this functor has also special notation, H and blank for the A. So what's this?
From B to A.
And what it tells us about this functor? So this is fully faithful, FF for shortness. So another way to formulate Ioannidis lemma, when you take this second functor to be a very special, again representable, you can say that Ioannidis lemma says that embedding of a category to the category of functors from this category to the sets is a fully faithful embedding. Just reinterpretation of what we already know. And the third remark about Ioannidis lemma, you can prove the same thing for the C, well, hat. And this will be the category of functors from the C op to the sets. So contravariant functors. So then in this category, you can try to compute HA and some contravariant functor F, and the answer is still the same. And of course, everything is natural. So this is for any F in the objects of the C hat. The same proof works.
Как второй пункт связан с lemma Ioannidis?
Well, we have this natural embedding of one category into another, just taking object and mapping this to the representable functor. We want to understand what's the Holmes set between two HA and HB. By the Ioannidis lemma, this is the answer. Well, I need to write H sub B of A, right? That would be an answer by the Ioannidis lemma. But this by definition of the HB, which is this thing. So the Holmes between two such functors are exactly the Holmes in the original category. So this means that this is fully faithful. So this functor preserves the Holmes sets. Okay. And finally, definition. So a functor is representable if, so a functor, say f, if there is A in the category C, such that f is isomorphic to the HA. So before I was saying that representable functors are these functors HA. Well, this is true up to isomorphism. So if functor is isomorphic to HA, it's also called representable. So in some sense, representable functor is a pair of data. So object A and also some natural isomorphism theta. Okay. Just a few remarks about Ioannidis lemma. Now, there was a question and we never answered this question. Maybe we can return to this. Say this is problem 0. Show that, so part A, identity is unique, and part B, F inverse is unique. Very simple warm-up exercise.
Some category for some object.
Yeah. We have a category, we have object X in this category.
And just compose,
Hmm?
Just compose. So,
No, do the exercise on the blackboard.
in this definition, we assume that functors from the sets, right?
Again, a priori, this is from the sets. A functor from the category to the sets is representable if you have this. But of course, you can do enriched versions if you know that your home sets in your category are just large, well, more interesting than just sets, some vector spaces, modules, etc.
So these are morphisms.
Well, this is setup of the beginning of the previous lecture. So we have category C, we have object X in this category C, then the identity is unique, and the inverse of any map is unique.
Okay, these are morphisms.
Ну, вы спрашивали, можете выйти и рассказать. Mhm. And that's exactly the computation you do in the beginning of the first year when you study groups. Okay, so maybe before we do problems on natural transformations, let's maybe discuss some functors. So in the next problem, you need to explicitly show that center of a group is not a functor. So Z, this is from the category of all groups. Well, again, say to the category of all groups. I can say abelian groups. So, but this is not a functor. So we need to find the problem with the definition of the center.
How does the background work?
No, you,
What should you prove that it is not a functor?
Yeah.
well, for example,
Like the map between objects is clear, but what about the map more?
Мы можем вложить группу больше, куда центр меньше. Тогда не удастся на центр.
yeah, so that will be one of the explanations. So any way that you could come up to define Z of some F won't work because you can provide an example.
We can say
Cannot we like map all maps to zero maps? Wouldn't that be a functor?
No, I think what you need to do, so suppose you know that this is a functor. Suppose Z of the group, well, this is center, and you have some map, and suppose, no. Suppose you somehow define this thing. Maybe come up with some rule to how to define this. Well, you need to check that no matter what definition you choose, you still get some problems.
Well, if we define Z of F to be the map which map everything to the identity element of G prime.
That would be just one particular map, one particular choice for the Z of F. And I'm claiming that whatever you choose for the Z of F, you still get a problem.
And
Well,
if we choose it to be like that, we will not have a problem.
Well, what's the problem if we send all the morphisms into the trivial one?
Ah, you say
all
you
the
say.
compositions will be okay.
Yeah. Just I think.
Maybe we're just trying to struggle with formalization of some natural idea, but we cannot somehow induce a functor by restricting it to the center. But maybe we just don't have to find a formal way to say it.
Or maybe we should just suppose that if we have non-zero, morphisms, that center sends it to non-zero morphism.
No, maybe we can assume something even more. Is that if you have an isomorphism of groups, you have an isomorphism of centers.
Well, actually, there is something wrong with definition.
Yeah, because if
Identity map has to be mapped to identity map, and then, for example, if you choose the trivial isomorphisms equals to each other, you will have a problem.
mm-hmm.
Ясно, что мешает изоморфизм, и все остальное.
Мгм.
В итоге это тождественно выражение. Но центр здесь это 2. Тут тождественно не получится. Потому что оба своего элемента.
Да. Yeah, I think, this is what kind of I expected. Sometimes something like this. So no matter how you define this C of F, you still get a contradiction. Okay. So next question. So we have a functor between two categories. So is image of F a subcategory in the category D?
У нас 2 первых задачи.
Huh?
Композиция сохраняется, ассоциативность сохраняется, единица сохраняется.
Yeah, so why this is a subcategory?
Well, because we only have to check that the identities are there and compositions are there. Exactly by the properties of what needs to be a functor.
And how do you know that the compositions are there?
Well, because functors distribute over compositions.
And so I think this is not enough.
То есть вроде как никто не обещал, что как бы новых равенств не появится.
Проблема с тем, что композиция лежит.
We only need to check that it is closed under taking composition. Other than not
Or we can try to construct maybe some small explicit examples with small number of objects and
F это F от B, это F от A на B.
Mhm. And this is not enough. Okay, let me say it like this. Give an example of a functor such that the image is not a subcategory.
Well, we can consider these silly examples of two categories. One is this kind of let it be pole set, and this thing. I obviously do not draw lines which correspond to the identical morphisms, but my idea is to glue these two lines the way that they will not. We can place it here and place it here by obvious correspondences. We send this object to here, this object to here, this object also to here, and this object to here, and identities go to identities, and these arrows go to this. But the point is, we won't obtain a subcategory, because if we did obtain the subcategory, which contained these two arrows, which the image obviously does contain, then we would necessarily would need to contain their composition, which we do not contain. So that's not a subcategory.
Yep, that's a counterexample.
And if the map between the objects is injective, is it a map?
If what?
If the map between the object, like if F, like of objects of C to objects of D is injective, would it be a map? So sort of emission Sabah. Like,
Isn't it injected here?
Or maybe
obviously not injective.
you take this
Oh,
two.
injectedness of on objects.
Yeah.
I mean, isn't the on the essential term? Because here we have the, the main problem is that we just don't have
Mm-hmm.
the arrow because of like some objects are not equal.
Yeah, I think that.
I think it's true because the image of a map, a function which is injectable objects is.
Yeah, I also think this is true. So this.
Что все готовы проверять, после этого.
Well, that's the homework. So next two properties are kind of interesting and easy to show. F in any category is monomorphism or epimorphism if and only if when you apply, well, I won't be able to formulate like this. So this is monomorphism if and only if H upper A of F is injective, and this is true for any A, for any object. So this is part A, and part B, F is epimorphism. We have a dual condition. So this is surjective. And this is again true for any object A in the category. Mhm.
Я запуталась в определениях, я уже ничего не понимаю, извините, пожалуйста.
Can I? Or maybe someone else? Yeah.
Well, I can.
Well, no, I'm sure you can, but maybe someone else wants. Well,
What is the difference between top A and lower A? Like, is it like just difference of
Ну, одни это полиморфизм из А в Б, а другие из Б в А.
no, we have this op of the categories. Essentially, you can say that if you can prove A, go to the opposite category, then B follows.
I guess you can try that.
I think that would be a problem because A is fixed as an object. You probably want something like x and y.
Yeah, so these are just objects in category C, and we want to show that HA tab, which is covariant to
No, this is covariant functor. If you're trying to prove B, this is covariant.
okay, so covariant. This is just normal one, yeah. Right. And so the epimorphism means that we have
So I'm not sure that I understand what you have here. What is this? F of x, f of y.
Not this, and this. Oh,
Ah.
no, wait. It's HA is in sense. Right?
Maybe you should just see how functor acts on
No,
error.
this is not the functor. The functor is
Yeah,
this is HA.
Yeah, HA. I mean, I wanna say where it belongs, like this map. This is map, right?
Mm-hmm.
So I wanna say it goes. Yeah, it's still here, I guess. Yeah.
No, but the problem is with this f applied to x and y. This I don't understand. Probably you want to write HA here and HA here also.
Oh, true. Yeah. HA of x, I guess. Yeah.
Mm-hmm.
Sure. That shouldn't matter.
Yeah, and this is in sets, yes.
And that's in sets, yeah, because it's homes, right?
Mm-hmm.
Yeah. Okay, so and so what do we need to check? Oh, this is one and two. And I guess just want to say that we want to check that this is two equivalent, so we need to give one. Then we want to check, we got that adapt as subjective, so let's try to first go like from here to here, I guess. So we get that, we know that adapt is subjective, and that gives us so we know that.
No, I guess the key thing here is actually to understand what precisely this thing is doing.
Yeah, it maps. So so it's morphism between HA of x and HA of y. So it's a morphism between yeah. So we have all range of morphisms, right? Of this thing as sets, right?
Mm-hmm.
So I guess we want to somehow deduce from that that we have a map from x to y, right? Wait, so HA of x again. What about it here? It's a morphism from A to x.
Mm-hmm.
So let's say we have some morphism, right? And we say that from that morphism, I guess we can get any morphism of that set, HA of x, right?
Let's do this a little bit differently, just to fix some notation. Maybe it will be easier to understand. So we can just write, say, HA of F, right? So this is as a functor supposed to be a map from the category C, say between Y and Z. Probably this is the interesting situation for us, right? So this will be a map sets. So here I'm supposed to apply HA of Y, right? But HA of Y is just maps C, A, Y, right? And this is C, what we have, A again, and Z. I'm just explicitly writing the same formula. And what this precisely we're doing here, so suppose I have a map G that lives in this home set.
Why do we assume homes of X, like either to Z? Shouldn't we like
Is this HA? I think HA is just HA without the because HA of F is a morphism.
I want to understand what this functor is doing on the morphisms, right? Well, yeah, notationally you're right. So
F like should be here maybe.
yeah, so I need to write it like this and say that I have element F. Well, F, do we want F? Maybe some other
I think we can use G.
G, maybe. Yeah.
I guess we're just not using X.
So can we just explicitly write this G goes to and where it goes?
Alright, well, according to this, so we have it's going to so J is from that. We need to go, so it's so we just compose every morphism from here with J. Then
Mm-hmm.
we get the map to morphisms from A to Z. So
Yeah, I would write it like this. T goes to the composition T with the,
here J.
and this is for any T living here.
Yeah.
Okay, so this is an explicit description.
Yeah, and we know that it's just subject, right?
Uh-huh.
So, oh yeah. Yeah, okay, so but here we have some kind of F, no? Or should you just have just HA is subject?
Mm,
You should just take G to be equal to F. Get
HA. Oh. Okay, so that, I mean, this is subjective and we need to show that F is empty, so I'm not even sure. So we want to consider this. And then,
I think it actually shows that F is mono. Maybe other way around. Well, F is mono means F is cancelable on the left, right?
mm-hmm.
Well, here we get exactly, no, if we
Oh,
get
it's
G
just
by
not
F,
that.
we exactly get cancelability on the left.
Okay.
So it actually should be the other way around.
When we finish the exercise, we'll see what's the correct answer.
So I just don't really understand what's happening now because before we had some F, which is, I believe it's some morphism between two objects of some category C, right?
Mm-hmm.
And HAF is a morphism between, so yeah, between HATX and HATY, right? In the category of sets. So I believe it to be subjective by means that HA of X, like a normal morphism from HAX to HA over here, right? So just the image of HAX is subjective, and here we have something else, I believe, no? Essentially, a different, because here we have some. Oh wait, there's some concrete morphism, right? Because we just have a
No, we did, but we
just
changed
have a function.
notation for some reason I don't
I
understand.
mean, yeah.
This is supposed to be f, right? If you want to, the same notation is in the problem.
Yeah, but we know not that this function is subjective, like it's not subjective like between these two sets, right?
No, that's a different condition.
Yeah, it's a bit confusing, right? So we know that the f is subjective, right?
Mm-hmm.
So it basically means that HAF, what it does, it goes like C to the F composition of C, right? And this map should be subjective, right?
Mm-hmm.
Like this map, yeah, or we just say that this map is subjective. And yeah, and it means that what it means. Now I want to say that it's empty, so it's morphism, I guess, either can Z, and we want to show that it's now set, right? So for
Можно
F,
сказать, что мы сейчас докажем, что он мономорфизм. Типа, если мы берем две разных Т, и они равны, то их прообразуем.
the task says the
То
opposite,
есть он
right?
мономорфизм.
Maybe I just confused the injective and subjective.
Это тут так.
Let's try to prove that it's mono. So we show like this, right?
Mm-hmm.
Okay, so what we have, we want to say that actually I don't see.
Well, in the second point, it should be injective too, I think, because of home is a left exact functor, not right exact one, no?
So you want to say that in the both conditions we need injectivity?
Looks strange, but I mean the first one is obvious about monomorphism.
Yeah, but I think it is wrong. As stated, it should be F is A should be F is active, if not if that thing is injected.
This is in B.
No,
That's probably
no.
You're talking about problem B, right? In problem B, you want to replace surjective by injective.
No, then you have to also replace lowercase a by
They both have
lower
to
a
be
by upper a.
injected. Because,
Well,
yeah.
can I have just
Okay.
write down? So
In the definition of monomorphism, epimorphism, we have some condition that two things are equal, therefore some other two things are equal.
Mm-hmm.
I'll start.
This is not in
I'll start
subjectivity.
with A. So suppose
Yeah, that's what I was trying to ask. So you need to put injectivity in A and B, right?
Yes.
To get the correct statement.
Yes.
but that's
And
yes, but it will still
and
I believe it will
functors
still be wrong
inappropriate.
because F is mono. Well, let's see what the condition in A means.
Mhm.
So we consider HA of F. What it does? Well, let F be a map between X and Y. So then we have the set of all maps from Y to A. Well, this is HA of Y, right?
Mm-hmm.
And here we have a set of all maps from X to A. This is HA
maybe we can just write this, that this is precomposition with F, right?
Yeah, so the other way around.
Yeah, precomposition, yeah, okay.
Yep. So now, what this thing is injective. Is equivalent to the fact that for any maps T1 and T2 from Y to A, we have the following statement, that F after T1, no, T1 after F equals T2 after F, then this implies that T1 is equal to T2, right?
Mhm.
But that is exactly the condition for F to be an epimorphism, because, well, epimorphism is cancelability on the right. We have the following diagram. We have
No, I think that
X,
this is clear that this is epimorphism.
T1, and then A.
So in Mona there is also mistake of the same type. I mean,
Well, I
H.
believe just if you completely, now, if we replace here mono by A,
No.
So no.
and
State.
now if we completely dualize the statement, what we gotta obtain is F is mono, if and only if the lower,
Is
well,
injective.
well, I believe it should be like this.
Surjectivity, there is should be injectivity in both cases
Okay.
because we have cancelability.
Maybe then we can, maybe this is equivalent to this statement.
I doesn't think so. Cancelability is just a condition about injectivity. You cannot take subjectivity from it.
Yeah, I agree with that. So the condition should be, this is cancelable on one side, so this is precomposition with one side, and this is cancelable, and this is just precomposition with the other side. So
What's the right confusion?
Hmm?
F is
Эпи.
or A?
Эпи.
So I think
Так главное в правильном порядке функции выбрать, в каком прекомпозиции, в каком посткомпозиции.
And injective.
Well, it's written on the blackboard.
Инъективность, инъективность аж сверху равносильно инъективности аж ниже.
нет.
Ой, в смысле, если свойства в этой самой в образе категории всех, как она по-русски. Все поможет.
Проблема в том, что один функция контрвариантна.
Если вниз поставить, то будет условие.
То есть он уже из определить категории берет. Если вниз поставить, например, А и B поставим, понимаю, да?
Оно десятварно надо.
У тебя вопрос ну, то есть,
Окей. Okay, so this is problem 4. We can define the center of any category as all natural transformations from the identity functor the identity functor and show that center is commutative.
Естественное преобразование можно представлять?
М?
Имеется в виду, что естественное преобразование можно представлять?
Можно так сказать.
А равенство в нат у нас буквально?
Это, кстати, изоморфизмы или просто?
Это все натуральные преобразования, все естественные преобразования. Я думаю, что да, просто обычное равенство.
If we consider monoids as a category, what would be natural transformation from it?
Conjunctions?
What?
Conjunctions? No? Движение элементов. Или
Why should it be called?
я пока не понял.
Есть какое-то одно преобразование Алина. We can consider such complete diagram and we have an natural transformation alpha.
Мгм.
So we can take y x and s is one natural transformation beta. So we have this is a function from x to x, morphism from x to x. And from this diagram we have that it means that this is commutative.
Мгм. And also there was a question, what happens if we have only one object in the category?
То есть для группы это правда центр должен быть.
Для моноида? Для моноида ответ понятный?
Ну да.
So is it clear for you?
And natural transformation from identity. So that way.
So what would be the question if C is just a monoid? Just the center of this monoid, yes. Okay, so now I think we can work out some details from the example from today's lecture. So we take commutative rings.
Sorry, again, about monoids. You asked what is center of monoids?
I asked, suppose that C is just a monoid, so category with one object. So if you just compute the center using this definition, what's the answer? The answer is center of this monoid. So groups, here we have GLN, this is determinant, GL1. So we need to show this is actually natural transformation. So there is a commutative square. Okay.
Well, what we want to check is that that is indeed the natural transformation. And the point to make here is that that's basically the thing that we did when we were in the first year. And what we did is we checked that when we have two matrices, here we have GLN and GL1, and these are somehow connected to n by n matrices here, and here it's just GL1, which is a multiplicative subgroup of the commutative ring. What we know is that, generally speaking, not only for n by n matrices, determinant is multiplicative, and my point is that that's actually what we need. Let's check the formal side of this statement. We'll do it the most straightforward way. What we have here, we wait 1 minute.
So the only thing you need that determinant is polynomial.
Yeah, I agree. No, we also need that it's multiplicative in order to prove that it
Yeah.
is actually a morphism
Yeah,
in the
yeah.
category of groups.
Okay, I guess
Well, I guess
have to something that I have to see, and maybe work a little bit more.
Well,
Okay.
it is actually.
Mhm.
So, what we need, first of all, we have to understand how these functors work actually, because when we have to amorphism of rings, we have to
understand how to map GLN of A into GLN of B. Well, if we understand that, the problem is basically done. Because, well, how this mapping works? Well, as I think, we just take a matrix from here, and if this is F, we apply F to all the elements of the matrix from here. This will obviously be homomorphism of groups. Now, as was noted, determinant is multiplicative, so these two maps will also be morphisms of groups. Now, here we also have just the restriction of mapping F.
Maybe F star.
Maybe,
But
it's just F restricted. A star. So now we have to prove that this diagram commutes. Well, as was noted, determinant is a polynomial of matrix elements, of matrix coefficients. So, well, if we let's just take a matrix, say A, I, J. Now we map it to this way. We map it to a matrix with elements F of Yj, of Ij. Now we map it to the determinant of F of Aij. Well, but this way around, we map it first to the determinant of Aij, and now I want to say that F of the determinant of a matrix is just the determinant of a matrix with coefficients which were entered by F. But this is obvious since the determinant is a polynomial.
Yeah, polynomial with integer coefficients, yes.
Можно так матрицами, еще без базиса определить отражение в G?
Well, yeah, I believe you just have to. Well, what is G? It's an automorphism of AM, right? So what we actually do here, and this is and this thing is automorphisms of Bn, which is the same thing as automorphisms of B tensor AM, right? So this map actually, how this map works, it takes F from alpha from here, and it maps it to identity on B tensor alpha.
Это трансцентральное произведение, оно развивает не только
F.
Well, let me just clear some space to write it down correctly. So we want to. I want to describe this map without the basis. So I believe that it works like this. We take something, some automorphism from here, and map it to.
Well, first of all, there is a little problem here. If you write it like this, you already assume that you choose a basis.
Yes.
Потому что у модуля, да.
Well, I would.
Make sure it doesn't
It's a free module
too much sense.
with of rank n.
And what if this is not free?
But what is JN? What is the group name?
Still invertible, maps from the module to itself,
Which module?
some module.
Не, ну погодите, это же все-таки из колец в группы, так что нам нужно как-то зафиксировать, во-первых, какой мы модуль от кольцом берем.
Yeah, with the module is fixed. Sure.
Сначала функтор в модуле.
We fix the module, so this is a module over A, right? So then we probably can define automorphisms of this module, right? So this is
understand. It involves a choice. How do you define a functor then?
this M is fixed, and instead of the GON, you just use automorphisms of M. So this will be a special case if M is a free module of rank N.
So it will be a functor from A algebras actually, right?
No.
Well, how does the functor work?
You mean the problem is that we need to choose also kind of functor for module for any ring.
So it should be just an abelian group then, and it should map B to automorphisms of B tensor tensor M.
No, abelian groups is not so interesting. Maybe we can do something like we take a vibration of all the modules or all the commutative rings, and then we fix a section of this vibration and define this diagram for any section of the
What is this
commutative rings
and this?
modules.
Which?
All modules or all commutative rings, and you take, well, maybe modules plus.
What is the morphism between module over 2?
What is
So this is a pair commutative ring and a module of this commutative ring, and here just forget half of the information.
Well, yeah, then that would work.
Yeah, but that's kind of an abstract picture of this. Yeah.
Тут придется доказывать, что это функтор.
No, the fact that this is a functor is clear.
Yeah, but you still have to define morphism here. It should.
But what did we achieve actually by doing this?
Well, a coordinate-free exposition of this computation.
It looks like a strange way to solve a strange problem.
No, the problem is that this depends on the basis, right? So if we say, if you want to avoid the basis, we need to say that there's a free module, right?
Yeah,
But
Yeah.
let's
I actually think if we just state, well, stay with free module, then the construction, I suppose, actually.
But there's nothing wrong with working with some coordinates, because if we want to work with the automorphisms of some abstract free module, we have to fix some free module. And how do we fix it in more general way when just taking A to the power of n?
Well, that's what I'm trying to avoid. I'm trying to choose a particular module over each ring by saying that there is a section.
Вот ты там написал вот это, а F там где участвует? Есть фантазм в конце.
Well,
Я не вижу.
how do you take tensor product of B with
Ah,
an A
понял.
module?
Понял.
The structure of B module here is in this way.
Объясни, пожалуйста.
В смысле, B это А модуль, потому что есть отображение.
I think this works.
No, this definitely works. But it's also an interesting question how to do this if you want to replace GON by automorphisms of some module. So the problem how we choose this some module. No.
Well, it looks like a proper generalization, since if we it works in this case. because-
Yeah. So for an example of section that I have in mind here would be, for example, section Sn, that on each ring, commutative ring, just choose a free module of rank n. That would be an example of such section. But potentially you have some other sections.
Тут, если отвечать на этот вопрос, то это надо описать, какие сечения
Не так.
задают нам вообще функторы.
Нет, сечения по определению функтора.
Нет, в смысле, это, конечно, функтор, а я прошу прощения, а вот перевод в автоморфизмы над тем, что выдает сечение,
Сейчас, по-моему, это будет функтор в категории групп по-прежнему.
Well, actually, that might be a problem because not polymorphism of modules. This is morphism of automorphisms.
Yeah, but here we don't have any, just two modules. We have kind of, they are sections of some, well, this is S of A and S of B. So they can be choosing in a consistent way. So maybe we can extract some information from this. Okay, so anyway, that's not a problem that we're going to do on this seminar. Maybe we can discuss some equivalences between categories. Maybe we start with the following question. Can you give me an example of two isomorphic or two kind of non-trivial categories that you've seen in some, for example, in algebra that are isomorphic, yes. Not just equivalent, but isomorphic.
The modulus.
Left are modules over A and left
Right.
are so something with taking a dual ring, opposite ring.
Yeah, so are modules isomorphic to the something like this. Yeah, I think this works. This is on the objects. This is just the identity, the same abelian group. We just reinterpret the data in two different ways. Oh, something else? Oh, this stands for the left modules, and I'm writing R on the left. And this is the right modules, so this is why I have R on the right. But left module is the same as the right module over the opposite ring.
На конечно-мерных векторных пространствах можно двойственность, но она же будет, получается, автоморфизм просто.
То есть здесь оп относится к R, но не может относиться к категории.
Да-да-да. Вот так.
А если категория, то это неверно.
Нет.
You can also consider
Why are modules not equivalent to examples?
Well, to answer these questions, you need chapter 2 of this course. You need to know some limits and colimits. There is I think the correct statement would be, if you take modules over R, take the dual category, it can never be realized as a modules over some ring.
It's not abelian.
Well, it is abelian. Well, dual to the abelian is abelian.
I hope.
Yeah, but I still want to see other examples of isomorphic categories that you definitely know from the algebra course.
representations of group algebra and
KG model.
Yeah, so another example would be this one. Representation, say, over K of the G. And this is isomorphic as a category to the KG modules. Okay. Other examples? Well, this is true. This is an example of isomorphic categories, but this is not from the basic algebra course.
It may be tautological, but Z modules and abelian groups, at least in our terminology, we said to.
Yeah, I think this is true. Yes, that would be an example.
But maybe they are in some literal sense literally equal.
But in some sense, isomorphic categories, it means that they are literally equal.
Yeah, but in this case it seems to be even more
Objects are equivalent.
Не, ну как бы чем
No, a priori, this is well.
Нет, ну
This-
сейчас так глубоко отличается изоморфизм из модулей веб-либо группы и изоморфизм между представлениями и модулями надгрупповой алгебры. Мне кажется, что тут КГБ оно настолько же в некотором смысле то же самое.
Ну да, да. How about Galois theory?
Well, there was a category of subgroups of a Galois group and the category of intermediate field extensions.
Yeah, this I.
Contravariant equivalence.
Yeah. So we can say that, say, L over K is Galois, G is the Galois group. So then what we have? We have G sets, and inside this category of G sets I choose transitive sets, and this is isomorphic as a category to the notation L over K underlined, and this is intermediate objects. So K is contained in the E, and E is contained in the L. Of course, with the obvious morphisms.
What are transitive, you said?
Hmm?
What are transitive, you said?
G sets which are transitive.
Well,
There is only one orbit.
well, I don't believe it is straight isomorphism of categories then, because from one subgroup, when we construct a whole proper class of G sets, of transitive G sets with
Yeah.
stabilized
How you suppose? How you do? If you have a transitive G set, then this is always canonically isomorphic to the G modulo H.
Well, isomorphic, but not equal.
Мы же можем совлечь там.
So, because I mean, the left category, I believe it has, well, at least infinite set of objects.
Ну, правда, тоже может быть бесконечной.
And the right one,
Правый,
even if we're
Если
talking about
конечно,
finite
да.
Galois extension, the right one is obviously finite.
Окей, то есть
On the left, there is no reason for this set.
Да,
Yes,
но
but
выбрать...
sets may be
Да.
isomorphic, but not equal.
Ну, возьмите скелет, господи.
Да, но множеств очень много, можно на куче одинаковых, по мощности.
Короче, берется скелет.
Yeah,
This is-
I agree. If we take the skeleton of
Skeleton definitely works, yes. So yeah, maybe we add this. Or we can naively just consider subcategory of subgroups of G.
What is the isomorphism here? Like,
well, and it should be also op somewhere, right?
Yes. Okay, so of course now there is a question. Let me do the following. So I want to remove the skeleton. I want just to take G sets, still transitive, opposite, and weaker statement that this is equivalent to the same category.
Ну, если его скелет...
Если эквивалент,
то, конечно,
No, the question I want to ask is different. What if I replace transitive here? How I need to modify the category on the right hand side? This is not a question for now, this is a question to think about. There is still an equivalence of categories, but on the right hand side you don't just get all fields. Just, well, you have some larger category. Yeah, and for now I want to solve the following.
Well, we can take the sum of the sum of extension because the
Well,
non-transitive action
What's the sum of extensions?
I mean, it's without field, but
But a couple of
Их
fields, or
зависит
triple
от
of fields, or something like that.
Не, там
A
их
reaction is the sum
зависимо.
of transitive actions.
Yeah, so probably one.
Зависимо. А
you-
когда транзитивно, там один и тот же элемент, он фиксирован одновременно во всех классах.
Well, probably you want some sort of algebras over K. No, not here. Here. Instead of just fields, you want some algebras. And you can understand the conditions that you need to put on this algebra.
Я не согласен. Бывает, например, что ну, если вот прямые суммы брать, то ну, возьмем прямую сумму двух одинаковых полей. У нас может на одном что-то, ну, вот группа Z плюс 2Z действует на 4 элементах, там нейтральный элемент понятно, как остальные переставляют под пары.
Mhm.
А автоморфизмах у прямой суммы двух полей будет 4. Ничего не переставляется, это переставляется, это переставляется, оба переставляется.
Well, we're not,
А чему это противоречит?
we're not talking about automorphisms. It's just a
Wait.
category of objects where case of integrated extensions.
Сейчас, ну, все равно же 4. Какаш, Введение, Вихар,
Is this true or wrong?
сейчас там эквивалентно написано, не изоморфно, да?
Да.
Но мы же можем еще раз оп взять, нет?
I'm asking, is this a correct statement? I'm not trying to prove this, or maybe not to confuse you. Is this a true equivalence of categories? Можно ручку? Well, in some sense, yes. Maybe you can use some very elementary limits.
Well, I
Да,
believe,
да, да.
I believe I can do that then if I.
So what you need to use?
Саша сейчас отвечал. Мне звучит быстро, значит, у нас же, если есть эквивалентность, то она дает реакцию на значит, морфизмах, значит, условиях полной строгости. Тогда, ну, вы заменим эти штуки на скелеты, останется просто по одному множеству каждой мощности. Тогда, значит, ну, у нас получится просто графы, значит, с...
Про графы не понял. У вас скелеты оставят, конечно, в каждом множестве только.
Можно, кажется, можно просто взять типа x из одного элемента или из двух элементов, и тогда количество морфизмов просто в одной категории из x y и в другой разное.
But you don't know where the equivalents might be.
Yeah, so
А вот количество морфизмов равно 2, это сколько на этих?
Есть пустой множество, из которого много скрилов выходит, а такого множества, в котором только скрилов выходит.
это да, может сработать.
Well, I can try to present this solution.
Окей. Окей.
Странный понятие морфизма, если он на морфизмах объективен.
I'm not sure this will work, but let's try. I want to show that there is no equivalence.
Мгм.
So suppose there is one, f. Now, I claim that f of a singleton set is an empty set. Well, that is so because singleton set is characterized by a very interesting categorical property that every set admits
Одна
a
точка.
unique morphism to a singleton set. An empty set is characterized by the dual property that empty set admits a unique morphism to every other set. Now, by the same reasoning, we have that
Это мы доказали, что символизм получается пустой?
Мгм.
well, because this one, singleton has a unique property for any set x, there exists a unique morphism from x to a singleton set. Right? And for any set x, there exists a unique morphism from an empty set to x. And it is clear that these conditions, firstly, they characterize these sets up to isomorphism. And secondly, they are dual to each other. So that such a contravariant equivalence,
У нас только одно может из одного же быть?
well, they are all isomorphic.
Not just isomorphic, but isomorphic by unique isomorphism.
Извиняюсь, но просто после того примера, там, где образ категории, это не категория, уже не верю в то. Ну, то есть я раньше в это верил, а теперь не верю.
No, that is definitely true. You can use your method. You net embedding, for example. I don't know.
I think this is much simpler. If you have any, say, consider general situation, any category. If you have a situation,
Initial and final objects have dual.
Initial and terminal, yeah.
yeah, but we haven't defined this yet. So suppose we have a situation where you have object and, well, we can say that cxt that has cardinality is exactly 1, right?
For any x.
For any x, yes. I think just from this condition we can immediately determine that if you have two such objects, well, I'm not going.
Well, if t prime is another such object,
Yeah,
then
so if you have two objects t and t prime, then immediately they are isomorphic, right?
Yeah.
Well, that is because you can just plug in t prime here and then plug in t and t prime. So there is unique map like this, unique map like this, and the composition is a unique map from t prime to t prime, and since the map is unique, it just has to be identity. So they are unique up to unique isomorphism.
Нет, в это-то я верю. Я не верю в другое. Ну как, не верю в то, что, точнее, я не понимаю, почему, когда мы поменяем, вопрос другой будет.
well, because it is
Ну,
fully faithful and essentially subjective. Well, because it is bijective of one. So, okay, if we believe this, now I would like to consider the following thing. The sum, the disjoint union of two singletons is two-element set, which is not isomorphic to a singleton. Whereas if we take product of two empty sets, we still get an empty set.
Nice.
So why does this prove that such F cannot exist? Well, because it is a contravariant equivalence. Thus, I claim that for any two objects, F of A and B, the disjoint union of A and B has to be mapped to the product of A and B. Well, at least isomorphic. Well, that is because it has a categorical characterization that
а можно вот какое-то доказательство того, что вот универсальные свойства там при вот таких штуках они действительно обращаются? Ну потому что, ну
well,
то есть,
it can be done by hand. So, what is the disjoint union of A and B? It's such an object that
окей.
Okay, so this is something that we're supposed to do in the next chapter. So
yeah,
maybe we can.
I don't know how to do it simply, but
What if you consider?
modular this equality, this proves that there
Не,
is
ну
another
кажется,
such.
того просто того, что пустой должен приходить в синглтон, а синглтон пустой, хватает, чтобы получилась просто не биекция, да? У тебя синглтон много, пустой один.
Так
Да.
не должна быть биекция.
This is
Нет,
equivalence.
А, прошу прощения.
Почему не годится, что в одной категории есть объект, с которого равно два морфизма, а другой нет? Ой,
Что за бред?
Okay, can I ask you a question? What are maps like this in the category of sets?
Oh, there are none.
Hmm?
There are none. There are no such maps.
No, what if X is an empty set?
Well, there is such a map.
I guess it's one of the situations where we have some freedom of choice what to include and what not to include in our categories.
Yeah, but we need one. I mean, identity element and identity.
No, I don't see any freedom of choice. So here everything is fixed. The left-hand side is completely fixed, and right-hand side is completely fixed.
Yeah.
Actually,
This is nice.
but that sounds a little bit artificial. The identity map from the empty set to the empty set. Well, it's what should be there if we include the empty set in the category of sets, obviously, but it just makes little sense in some. If we turn to common sense, what is a map from an empty set?
Well, I'm not sure that I understand
Well,
your
we can
argument.
make sense of it.
Well, if you want a category of sets, we have an empty set. And we have any object, we have identity map from this object. So it's necessary to form a
What is
category.
this argument actually?
I think we're seeing the details of the argument.
Yeah, so, so we observed that there are no, if X is an empty set, then there is only one such map, and otherwise there are no such maps
Mm-hmm.
at all. So if we have such an equivalence, then we have the following. Then we have the following equality, right? Well, this equality is just because equivalence is fully faithful, and this is just by definition of the opposite category, right? But if we take X such that, we can surely take X such that X is not isomorphic to singleton empty set, and f of X is also not isomorphic to these things. Something breaks here, because for any non-empty set, we have many morphisms.
Mm-hmm.
The singleton here, we have exactly as many morphisms from singleton set to f of X as there are elements in f of X. And now, if X is non-empty, then there is no such morphism,
Mm-hmm.
which is a contradiction.
Okay, I think we're out of time, so maybe the next question you can consider as a homework. If you consider bigger categories, is this true or wrong?
What's that?
Category of all binary relations. So that's it for today. And it actually an easy question. I think it's easier than the previous one.
В смысле, мы можем